All right, well, thanks everyone for coming back after lunch. I'm exide. This is Glitching for Noobs, a journey to coax out chips' inner secrets. And that title is pretty self-explanatory. It's pretty much my explorations over the last couple of years to, as a noob myself, basically try to figure out what is glitching, how is it performed, and what kind of interesting results can you obtain from the experiments. So just a quick agenda. I'll cover a large chunk on background, which is kind of the classroom stuff, what is glitching, electrically, what is it doing, and perhaps some countermeasures against it. Then a second major section will be the platforms, which are the different hardware I've constructed over the last couple of years, and the pros and cons of some of those different approaches of those platforms. And then some excerpts from a real-world example where I was able to dump a chip, basically secure microcontroller, and to hopefully get you guys thinking of good tactics and how to approach some of your own chips if you've been wondering about the viability of glitching. So about me, I'm an IT monkey by day, consultant, and hardware hacker by night. So this is kind of a side project over the last couple of years. I like designing and reversing embedded systems, IC security and failure analysis, arcade platforms, automotive stuff, wrenching on cars, ECUs. The whole kind of works on that side. And then there's my email at the bottom, exide31337@yahoo.com, if you have any questions or just want to get in touch. All right, so what is glitching? So let's start with our definition, our textbook definition here. Glitch is a transient which can induce alteration in device operation. So this could be, doesn't have to be electrical. It could be, as listed kind of lower below there, it could be laser, thermal, radioactive. But for the purposes of this talk, let's focus on electrical glitching, and more specifically on clock signal glitching and power or voltage glitching. So basically, there's three kind of classes of attacks on the little traffic light picture on the right. So non-invasive, semi-invasive, and invasive. So glitching is considered non-invasive, principally because it doesn't alter the device package physically, so you're not milling the epoxy or melting it down or decapping or anything like that. It doesn't permanently alter the operation of the device, unless for the first few tries where you're getting a little flamboyant with the voltages you're sending into the chip, but it shouldn't permanently alter the operation, meaning it's repeatable. You can keep doing the attack or sending the waveforms into the chip over and over again. It's surreptitious, so it means you can do it and there's no signs of tampering because, again, you're not physically even altering the package. Usually cheap. You don't need an expensive lab. You don't need specialized microscopes. And however, any background details coming into you approaching a chip are absolutely beneficial because glitching can be black box. And if you have a decap chip or an image of the ROM or any sort of physical indicators to help guide you what the chip might be, then you definitely want to apply those in your knowledge base about the chip. And it helps to narrow the scope and strategy of what you're doing. So here's some examples of non-invasive attacks. So under the umbrella of fault injection, there's clock glitching, voltage glitching, which I'll cover. Thermal, which is kind of, you could either, really what you've got with an exposed package is you've got pins or you've got the epoxy blob, right? So you could try and heat that up or heat individual pins, but it's really, I don't think it's very fruitful or very predictable because you're basically trying to heat the transistor, kind of like the transistor junctions, and Also, that epoxy package is going to have a lot of thermal mass, so it's going to take a long time to heat up, relatively speaking, and then a while to cool down. So if you're trying to hit something really quickly, send at a certain clock cycle in a chip, thermal's really not going to be precise enough. And radioactive, this is just theory from what I've read. I don't have a brick of uranium in my basement that I can rest my chips on top of, or any other gamma rays or X-rays or things like that. So the second kind of subfamily of non-invasive is side channel. So there's power analysis, which is basically analyzing the current or power consumed by the device in response to what stage of execution or operations the chip's doing. And actually Colin O'Flynn is going to be doing, giving that really good treatment, I think, on Sunday. So yeah, that will be something to look forward to, that talk. Timing attacks. Timing attacks is basically you're watching the response time of maybe control flow in a loop. If it goes to this condition, then it takes this long. Else, if it's doing some sort of other operation, it's going to take even longer or shorter. So it gives you some sort of cues what operation the device is doing. Data remnants, that is kind of like your cold boot attacks. And so kind of a point there is memory zeroization is something you have to be aware of. Most chips probably don't have that aren't security designed or purpose built, may not wipe RAM or other volatile memory in response to certain conditions, but some may. So that might be consideration that works in your favor if the device, upon reset or halt or whatever, doesn't actually wipe its memory. Then there could be some goodies still left behind. And then finally, the third subfamily is just your generic software. So just regular code vulnerabilities. So even though you're running an embedded CPU, it still could be vulnerable to stack smashing, buffer overflows, stuff like that. So there just may be bugs in the code that the developers aren't aware of. Brute forcing, so just in general, if it's feasible, trying to brute force, if it's a really small key or a binary value or 16-bit value or something where you're able to repeatedly try attempts over and over again, it might be worthwhile. And then finally, the last class there, backdoors, which may be your JTAG, or perhaps you hold a pin of the package at a certain low or high for so many milliseconds and it goes into a different debug mode, undocumented instructions, stuff like that. So the second major class of attacks out of the three is semi-invasive. So in this class, basically you can alter the device package, so you might completely decapsulate the device and still try and keep it running, or you may do backside attacks, for example, where you mill through the backside of the chip and get access to the bulk silicon that way, but you're not doing typically as hardcore stuff as die alteration. Like that's up a notch in the invasive class. So usually these ones don't permanently alter the device operation either. You alter the package, but not the actual operation of the device. It still doesn't know or care that it's been opened up and still behaves as normal unless there's like light sensors or UV sensors or things like that. It's usually repeatable unless you leave the laser on too long when you're pointing it at various transistors or fuses or areas of the die. It's more expensive, so yeah, you've got lasers, you can involve microscopes, chemicals, a mill, and this class of attack may be beyond a single person's budget, whereas the non-invasive is relatively cheap. And this class of attack provides you backing details where you may not have had them, whereas with non-invasive, anything you can know beforehand will help you, whereas this will actually provide you with information. You'll look right at the die and potentially get a floor plan or a layout of what's going on. So here's some examples of actual semi-invasive. There is glitching in this class as well, but now we're into laser or like flash, as in like a flash bulb or flash from a camera directed at certain areas of the chip can. There's some classes of chips where it'll reset security fuses and lock bits. Thermal in this case, which is kind of, I believe, would be a byproduct of laser, for example, where you're heating up, but now you've got the device open, so you're not trying to heat up the external bonded out pins, you're trying to heat up an individual transistor or area. So now you've got much more precision and can actually affect something like a crypto routine, etc. Laser scanning, there's unpowered versus powered device. That, I believe, is where if you direct some photons at a transistor that's off, for example, that's on, nothing's going to happen additionally. But if you direct photons at a transistor that's off, it will start conducting, I'm not sure fully, but maybe weakly, and that will be enough to present a current signature that you can actually see, like something additional gates are actually activated on the chip now and can give you some more recon. And then finally, there's the good old optical imaging. So you've got front side or back side, and you've got visible, which is just your regular objectives on a microscope, or infrared imaging, where you can come through the back side and get a layout and floor plan from there as well. So finally, the highest notch of attack class is invasive. And this is where your device package is certainly altered, and you're probably decapsulating, at least partially, or just removing all of the epoxy and having the die just sitting there. And it's involving die alteration at this point. So you're basically doing the nanometer equivalent of plasma cutting and welding, where you're depositing material and you're removing material, i.e. cutting traces or power traces or signal traces, or adding vias or test points that were not there before that give you access to a trace deep inside the chip. So this class of attack can certainly render the device non-functional, especially if you're imaging the chip layer by layer. You're pretty much using very scary acids that are stripping glass, basically. So the metal layers are coming off the chip one layer at a time, and you're going to destroy it, but you're going to image it in the process. Now, if you're careful, the chip can still run, not as part of the imaging process, but if you're just doing alterations and edits where you want to get to a certain data bus or address bus, for example, or a certain control signal, if you're careful with how you reach that part of the chip, it'll still run. So some of these techniques are one-time, i.e. a fib, whereas a fib workstation can create and undo edits. As I was saying, it's kind of like a nano scale plasma cutting and welding. So it just, however, it's just with most welding and bodywork type jobs on your car, it's never going to be 100% perfect and pristine as if when it was originally, the original photolithographic process made the die. So it can be costly, very costly. Decapping and readouts are reasonable, but the circuit editing is prohibitive pretty much unless you're renting time on the equipment. And finally, this can provide you with almost complete background details because you're at the gate level, you're looking at individual transistors, individual functional blocks within the chip, memories, things like that. So it's the ultimate in background information. So here's some quick examples of invasive techniques: decapsulation and delayering, memory, so ROM readout, doing ROM staining or just looking at the ROM. Sometimes you can just see from the contrast which are zeros, which are ones. Circuit edits, so there's etching where you remove, deposition where you add material, wire bonding where you're bringing signals outside the chip into maybe a more friendly package, like a big giant dip in comparison to what the actual die may have originally been bonded into. And you can purposely destroy traces or transistors at this stage by putting a couple microprobes down, for example, and putting high current across them or high voltage and actually blowing up a transistor that you don't like that's in the path between the two probes. And then finally, you can along those lines, you can microprobe both to sniff and to drive signals onto the bus. So you can listen and you can read and you can write. So getting back to the glitching side of things, the non-invasive side of things, Here are basically, I like to sit on my thinking couch in my basement, which is where I just stare at the roof for a while, and sometimes good ideas come to me. And these were the 4 methods that I could think of off the top of my head that I could generate a glitch pulse with that could be further usable for both clock or voltage glitching, depending on what you want to do. But you need to be able to generate the pulse in the first place. So the first is just a naive clock divider method. So you have 1 or more D flip-flops cascaded that are fed originally by a system clock, whatever you want. Here it's 48 megahertz, for example. After you go through one flip-flop, now it's divided by 2 to 24. Go through another flip-flop if you want to. Now you're down to 12. Feed that as one signal into the mux. Take the original system clock, feed that as another one into the mux. Now you've got a slow clock and a fast clock, and then you just use your select line on your multiplexer to switch between the slow clock and the fast clock. So basically this is what the waveform would look like. You've got a 1x clock, or just a 1-speed clock, then double that, and then when your select line goes high in the second half of that 1x wave, basically along this dashed line, you can see that now you've inserted a couple fast pulses where the chip may have been like right at this point, because at this point here on the dashed line, the chip's still expecting that that rising edge at that same time, but this second one here, it's going to be hitting the chip twice as fast as when it's expecting it to get there, basically. So, and I'll go into a little bit more detail later on that. So the next idea was to use a PLL if you have one, either a discrete PLL chip, or if you're using an FPGA, most of them are well equipped, where you just literally configure the PLL's outputs to whatever frequencies you want. They don't have to always be integer, well, they're integer, yes, but they can be multiplied up and divided down to give you kind of fractional speeds. But same thing at the end of the day, feed them all into a mux and use your select lines to choose which clock you want to blast the chip with at any given instruction cycle. Third method is what I call poly PWM, where it's just multiple pulse width modulation signals. And what you do is each PWM signal, one after another, has successively longer and longer duty cycles. And then when you run those all, so 50% duty cycle, 70%, 85, but they're all 12 megahertz frequency. It's just the widths are longer at that 12 megahertz. Feed them all into an XOR, and what you'll get is a glitch pulse, a small glitch pulse that you can again toggle between your nominal clock and your glitch clock, and it looks a little something like this, where your first wave is your nominal 50% duty cycle. Second wave is 60% duty cycle, so it's a bit longer, but still the same frequency. This rising edge here is still at the same point in all the waveforms. 70% duty cycle now. And when you XOR these top 3 waves together through an XOR gate, you'll get the overlap between these two. The distance between the duty cycle will give you the width of your pulse. And the distance between the 50% and 60%, the wave 1 and 2, is where that pulse starts. And the distance between this waveform 2 and waveform 3 is how long the pulse goes for. And then you can see it pulses once in the first cycle of the nominal clock, and then again repeats. And you can use your select line on your multiplexer to choose when you want to bring that in or not. Polyphase. So this is basically pretty much the same thing as poly PWM, except you are using phase shifting as part of your PLL. Like, I'm using Altera FPGAs, and their built-in PLLs allow you to phase shift right in the PLL. So all you do is you shift your waves 2 and 3 successively further apart from one another, XOR them in again, and you'll get something that looks like this. So it's really the same as the triple PWM, except it's doing it on the leading edges and the trailing edges of the waveform. So now instead of 2 glitch pulses, you get 4 in that same period of time. And here's just a little snippet from Altera's guide for how to configure the actual PLL. Basically, it's got these phase up and phase counter select, scan, phase step, scan, clock. There's all these discrete signals. And I wanted to just do it simple, naive, have some I/O pins from my soft CPU on the FPGA toggling these things. But the timing is so critical that I tried it and it didn't work. So yeah, this is kind of like an example. The details don't really matter, but of the actual waveforms you had to provide to get it to step the phase up or down in the PLL. And so I ended up just having to make basically a state machine that the CPU would assert a signal, this start equals 1, then it kicks the program off. This sets all those signals from this slide up correctly, then sits in the done state, and start is still 1, let's say, because the CPU is really slow, relatively speaking. It'll just sit there looping there, so it won't just keep all of a sudden firing off another phase shift loop, because otherwise it may be non-deterministic how many times it's actually shifting the phase, and at this point I want precision, not, I've all of a sudden got 180, or this time I've got 270-degree phase shift, or this and that. So it's just kind of, I needed to do that to keep the process straightforward. So what is clock glitching? It's a momentary burst in frequency. It's absolutely timing critical with respect to the value of the program counter. So it's critical to where the program is in its execution, or where the CPU is in its execution of the program. You have to do this glitch at somewhere advantageous, maybe a loop counter or a jump that you want to get rid of. It's the same as the software side. You're trying to get rid of the jump, maybe to in a crack me, to a bad dialog box. It's the same thing. You're just converting the jump to maybe an add or something harmless. And what's also important is the offset of the glitch within the particular instruction cycle that the CPU is on. Because that was this guy here, where the first and second waveforms combined allow you to set the offset of where in the that clock cycle the glitch starts. Then finally the duration of the glitch, which was that second and third waveform combining to give you the length of the actual pulse. So what's actually happening? The register or the flip-flops in the logic of the victim device are going to latch invalid data. And why they do this is because the signals are still propagating through a cloud of combinatorial logic. When you all of a sudden clock the circuit twice as fast, or whatever multiple as fast as faster than what the device was expecting, those signals haven't traversed from one set of sequential logic to another on the other side of the device by the time you've clocked it suddenly. And basically you're able to clock in invalid data into the destination flip-flops. So instructions are replaced with mutated opcodes. So they're not. So this is what I was saying, where you want to turn a JSR into an add, and it's like patching a software binary, but the instruction is not technically skipped. Effectively, it feels like it is, but it's mutated or replaced, not skipped. Like, it'll turn into something else. The program counter doesn't just magically skip ahead 2 locations, let's say, and you skip the instruction. It still clocks in those next 2 locations, but that instruction is turned into something harmless or advantageous. And another example is, like, if the security fuse or lock bit logic is slower than the rest of the chip, you may be able to latch advantageous values in the security fuse logic as well using a clock glitch, which may allow you to do things like unlock the read access to all of the memory map of the chip or things like that. So here's kind of a quick overview of the clock glitching phenomenon, where you've got the source flip-flop on one side of the die, let's say, and it's going to flow through a bunch of discrete gates, combinatorial gates, and then finally there's a destination flip-flop. And what's happening is, when you glitch, this blue line is where your glitch appears, and the end of the yellow dash line is where it would normally expect to propagate. But when you clock the circuit unexpectedly or quickly, you'll latch in a value at this point before the signal is actually propagated to where it needs to end up, which is this destination flip-flop on the right-hand side. So that's clock glitching. The mechanics of voltage glitching is basically a momentary reduction in supply voltage, and you're dropping the supply to or below the transistor switching threshold. And what this does as a side effect is it increases the propagation delay of the signal through the logic chain, because you're decreasing VCC momentarily, which decreases your FET gate to source voltage, and because of just the mechanics of a FET, it's reducing your current drive ability as well. And because you've got a lower current drive strength, this causes a slower rise time, and if you've got a slower rise time, it's going to take longer for the signal to propagate through the device. So that's basically why the propagation delay increases as you lower the voltage. And this is, like clock glitching, this is timing critical. You have to hit at the right part of the program, possibly at the right point in the particular instruction cycle, and you'll want to play around with the length of the pulse, the duration. So voltage glitching will allow you to alter values at the memory sense amplifiers during a read operation. So like if it's flash, E2 RAM, basically allows you to latch corrupt data onto, for example, the address bus or the data bus, which could be advantageous because you would latch a invalid instruction or an advantageous instruction, turning your harmful jump into a harmless add. And again, the security fuse logic can latch corrupt values in a voltage glitch due to the operation at or below the switching threshold. So you may be able to tweak the security fuses in your favor. So just to cover a few misconceptions, you're not throwing random voltages, sags, and surges at the IC and seeing what sticks. It's a very good idea to respect the absolute maximum ratings if you have a data sheet or if you suspect what family of logic it is. Still respect them for VCC, VCCIO. There are some specific families of 74 series that can handle almost limitless voltage swings. Like for example, I've seen a logic 74 gate that can take plus minus 12 RS-232, but that's because you're severely limiting the current going into that chip on purpose so that you're not going to damage it. Otherwise, if you're not thinking about things like this ahead of time, then do not put aggressive voltages. If anything, drop the voltage, don't spike it. You're not randomly jarring the clock frequency to wild extents. You're probably going to pick a very small amount of your slow clock and your fast glitch clock or your glitch pulse, and you're going to switch between those. You're not just randomly moving between multiple frequencies all over the board. And like I said, you're not skipping instructions. Technically, you're replacing or mutating them. The program counter still will count up one instruction at a time. Timing critical, I've covered that again a couple times. And then finally, unless the chip is stuck in a loop, random glitching is usually counterproductive. So if it is stuck in a loop, then yes, glitch randomly at different times all over the place, try voltage, try clock, because anything to pop the chip out of the loop will meet your goal. But if you're actually trying to do a specific thing like dump firmware or bypass a bootloader check, potentially you'll probably want to be more precise where you're actually placing that glitch over time. So sorry about the wordy slide here, but here's some of the advantageous outcomes that glitching voltage clock in general can provide you. You can make the CPU replace impeding instructions that are impeding your progress. You can do stuff like truncate cryptographic operations or keys. Sometimes as the key is written to E2 or flash, you can corrupt that operation. So now you've turned in a 16-byte key down to 4 or 8 potentially, and you can brute force the missing chunks of it. Von Neumann dumps can be exhaustive. So what that means is if the victim you're attacking is mostly von Neumann or some forms of modified Harvard, you'll actually get code and data in one relatively flat space, depending if there's paging or MMU or whatever, and you couldn't have the complete dump if you even pop it at a single location and you're able to loop through every address value. So this code extraction can provide clarity on internal operation, because now you've basically got the code. If you've got the full dump, you know what program the internal thing is doing and what branches it can take, what things its protocol handlers may be, what commands its protocol handlers may be looking for, if there's any backdoor commands, things like that. Secrets can be revealed, so your crypto primitives or keys, maybe a device serial number that you might need to know, S boxes, stuff like that. And of course, at this point, you want to scour for software vulnerabilities, because if you can find an actual buffer overflow sitting in their code that's burnt into ROM or flash, then if it's in ROM, they're not going to be able to fix it. So you can freely come back to the trough over and over again and exploit that vulnerability. It also, another outcome is you can do things like bypass bootloader and force checks. So stop the MMU or page tables from initializing. So let's say a device maps in a different actual runtime firmware after and maps out the bootloader. Well, you may be interested in stopping that process so you have access to the bootloader where there might be interesting firmware details or registers or things mapped in at that address space. Another thing you can do is prevent lockout counters from rolling. So if you've got a device, secure crypto memory, or any sort of device that has a counter that counts down, and when you're at 0, you're out of luck, the device locks up or wipes its crypto secrets or whatever. With glitching, if you starve the device of voltage or potentially clock glitching, you can stop the device from being able to write to that counter location. So if you have 5 tries, it just stays 5 because you keep hitting it right at the time where it's about to decrement the counter. And finally, as mentioned before, you may be able to erase security fuses or lock bits, which allows you to keep the flash and E-squared intact. And at that point, just depending on the pinout and the type of device, you could just maybe drop it into a parallel or serial programmer and read it out that way if it's a PIC or an AVR or something along those lines. So here are some targets of interest where glitching may apply to. It's kind of hand-wavy because I'm covering all sorts of stuff here, but you got general purpose devices like CPUs, microcontrollers, memories, DSPs. Custom devices like FPGAs and ASICs, I'm not including it here because it's a target of interest so much as a cautionary comment that pretty much good luck with an FPGA or ASIC depending on the implementation, because it can have whatever RTL code running in it that the designer chooses. So it wouldn't be my first choice to attempt glitching one of those devices, but the general purpose devices, some of the security, or many of the security enhanced ones, other than ultra modern ones where the manufacturers have wised up and fixed a lot of the issues in the hardware at the hardware level. So SIM cards, smart meters, military, chip and pin, pay TV, transit passes, automotive keyless entry, things like that may all be valid targets. So what are some countermeasures against glitching that could that could try and foil you? So basically, CPUs which halt or trap on invalid instructions can be helpful, but like I said, you're mutating instructions or replacing them. So if your type of glitch mutates a jump into an add's still a valid instruction. So you're not actually the CPU won't halt or erase its memory or whatever, depending on if the instruction, if it mutates into valid or invalid. Another countermeasure is you can erase volatile memory on startup or reset from the data remnants perspective. So kind of like Heartbleed didn't attack with the OpenSSL stuff, you want to minimize the number of copies of important secrets scattered throughout the device, try and just as a best practice. And if you can, wipe some of these primitives or secrets between iterations of the routine if possible. Some of them, they have to be long-lived and you're not going to be able to, but if you can wipe them, do so they're not sitting there lying around. Now from the clocking perspective, the clever security device manufacturers have decided to run off internal oscillators in many cases, so the clock pin on the outside is merely a suggestion. All it may do is actually kick the internal oscillator off, and then after that it runs freely on the internal piece. Sometimes you can use asynchronous logic if you don't need everything tightly clocked. And Another sneaky trick is to use aperiodic or random clock period generation, and that will add like things like dummy cycles into the clock that make it harder to get anywhere. So some further countermeasures in the supply voltage side have glitch or brownout detection that actually watches when the voltage drops too low and then either resets the device, ignores the glitch, or erases, does some sort of punitive damage back towards you. Low pass filter, which will just basically ignore that glitch. And then reset, halt, wipe the device. So many general purpose devices have little or no designed in protections. So that it shouldn't stop you from trying to attempt these attacks on different devices. Like AVR, PIC, MSP, TI MSP, for example, do have memory protections, lock bits, and stuff like that. So some of the manufacturers, they are trying. And of course, modern smart cards are relatively insane. They have glitch detectors. They have random asynchronous internal clock with dummy cycles, as I just mentioned. And they have, some of them have dual lockstep cores that are sanity checking one another. So if you're able to glitch an instruction on one core, the other core will detect that and cause a trap or a fault. So I got to quickly start blasting through this section. This is kind of some of the platforms that I attempted to make over the last couple of years, and what I was able to use them for. So basically, the first was the Aero low power reference platform board that I found surplus on eBay, coupled to a breadboard. So the LPRP basically has a Cyclone 3, Altera Cyclone 3 FPGA. I threw in a MIPS 32 soft CPU, my Poly PWM generation, my Poly phase clock generation, a good old 16550 UART, SRAM and flash drivers, and output muxes, which are just the muxes that let you select your clock, slow or fast, whatever. And the breadboard is basically just doing level shifting and signal conditioning to and from the FPGA. And here's a few of the highlights of the actual LPRP board itself, just USB connection to the host computer with a FT232 and a Altera CPLD, which acts as a USB blaster to load in the bit stream to the FPGA. Intel Flash and Micron PS-RAM at the bottom, which I had to write drivers for. The PS-RAM is nice because it's fast SRAM and good amount or decent amount of storage. I think it's 8 megabits on that board. So, and then there's an SD card if needed. The solderless breadboard details, basically it's pretty Mickey Mouse. There's a couple 74 LV125s. The LV is important. They are 74 logic family that is 5 volt tolerant. So I use one to drive out at 3.3, but it can accept in signals at 5 volts without blowing it up. And then the other one is running at 5 volts and can accept 5 volts or 3.3 volts. So it just uses converters going back and forth to the FPGA. DUT is the device, the victim chip under test, and then I just have on this board I had a pull-up pot to just change the strength of the pull-up. Here was another board which was kind of early on where I soldered up a hard version of the solderless breadboard. This one had a few additional components for mostly for voltage glitching rather than the other board, which is mostly clock glitching. This one has some analog multiplexers right here on the right-hand side. Same 74 125s. An op-amp buffer coupled to a ghetto DAC, which is basically RC low-pass filter going into the buffer, which you send a PWM stream, so a fixed frequency, different pulse lengths. And what comes out of the ghetto DAC is a varying DC voltage based on the fatness of the PWM wave. So it's just simpler than, if you don't have DAC or ADC hardware, just do that. And the buffer is just used to provide current sourcing ability. I played with an Arduino for a little bit for basic clock glitching, but due to the prescaler and how it generates the PWM and the output compare hardware, pretty much it automatically, you eat a divide by 2 switching to this. So if it's a 16 megahertz crystal that these things ship with, the fastest wave you can put out of it is 8, and wasn't really that flexible. This was my nightmare hand-etched, photo-etched PCB. My transparency mask was not quite flat on one edge of the pre-sensitized board here. So what happens is you actually you literally get an out of focus traces and stuff on the board. So you can see there's big, well, it's hard to see in this area, but there's chunks here that are totally etched through unevenly. There's traces missing all up in here. Dimitri heard me whining about my epic fails with this, I think. Areas here where it's already starting to eat through the resist of what was supposed to be a ground plane. Closer area there, which looks disastrous. So finally, I relented and went to Osh Park and made a this is a sideboard aside from the FPGA board that is designed for voltage glitching. And this incorporates a lot of the same elements, the ghetto DAC. This one has a fixed crystal mini USB connection through FT232. The FT232 runs in synchronous bit bang mode, which I found in the datasheet, and that allows me to basically bit bang the SPI pins so that I can in-circuit program the next slide, the AVR. That's a AT-Tiny. I just grabbed an AT-Tiny 2313 that I had off the shelf from like 10 years ago. Other than that, the rest of the hardware is fairly similar. This was a quick little sniffer board I made that is just literally a 74 AHC 125, which is another variant of 74 that can handle, can drive at 3.3, but can accept as input it's 5 volt tolerant. So just a quick way to sniff, to man in the middle my device under test and get the signals from it into the FPGA board. And something I'd like to highlight, if you guys are using FPGAs but don't know about it, Altera Signal Tap 2 is a great cheap and dirty logic analyzer. What it is it's logic that gets baked into the FPGA bit stream, but it's also a software piece, part of Quartus, where you can actually pull it up, and what you do is you can select almost any internal signal, net or bus, and external pins, so those will be your pin icons in your actual top-level design, and allow you to capture the data on those pins and store it. So, and you can increase the sample depth, how much you want to store by using more logic elements or Xilinx slices. You got plenty of trigger options, simple and advanced. You can export the data as plain text, as image, as other binary waveform formats, and it's equivalent to Xilinx chip scope, but I'm not really a Xilinx specialist, so I don't know the exact comparison. So this is just a quick shot where you can select the signals you want to watch, select the clock at which you want to clock signal tap, the reference clock, and then you can actually see here I'm watching a slower clock down here, and this is actually that state machine I made to program the phase shift up or down on the PLL. So into the last section. This is my real world example. So I had a Victim IC. It was a secure microcontroller. I didn't know what architecture it was. So this is pretty much a black box approach. It pairs with a partner device which it interrogates it, sends it commands, and expects responses. I know that it accepts data, encrypts and decrypts it with keys, and then returns the data back to the partner device. And I don't even know what data sheets to look for because I don't know what it is. And even if I did know what it is, the data sheets might not be public. So what I did was I started probing the device pads. First, sweep with a multimeter. Just some of the flukes, for example, you'll see the little bar graph at the bottom of the fluke will flutter rapidly, a lot faster than the actual digital readout, so you know that there's some sort of semi-fast signal there. And then the next process is to revisit the interesting pads with an oscilloscope to get an actual handle on what's the nature of the signal. And I noticed one pad appeared to speak a slowish serial protocol. So I've got an older tech scope that doesn't have hardware protocol decode and has a floppy drive basically, so kind of useless. So I captured and just transcribed it by hand for the first few bytes. And there's one physical pad on the victim chips, thus, and I noticed it looked like it was sending and receiving, so it was like a half duplex conversation, so there weren't separate RX and TX lines, it was both in one. So what I did was I rigged up the sniffer board to man in the middle the victim to partner conversation, and all that board is just doing level shifting and buffering of the signal. I took that output into Signal Tap to digitize the conversation, which I could have done if I had a nice fancy scope that can do that. Now I could export the waveforms as plain text, like a 1, 0, a 1, 0 over time, and then I can pack those ones and zeros back into binary data by kind of parsing that stream. And what I found after a bit of looking is that I actually had a match on an ISO 7816 APDU header, so it meant it was smart card 7816 protocol. So then what I did, now that I knew this, is I bolted a UART to the FPGA and soft CPU in the FPGA, and this allowed for hardware framing of the transmit and reception of data with the victim, so I didn't have to basically screw around bit banging and having to get the timing perfect. Then I used the unrelated Altera's JTAG UART, which is a separate kind of out-of-band UART, part of the USB cable, allows you to talk with the soft CPU. So what that does is, otherwise you would need a separate programming the FPGA versus talking to the soft CPU cable, whereas it's nice to just do it both on one cable. And so what this does is allow the PC to talk to the victim device using the soft CPU, the MIPS 32 CPU as an intermediary. And so the next thing I was reading through the spec, ISO 7816 header has a length field. So part of this process is you have to make hunches, and sometimes it's a hunch chain to a hunch chain to a hunch that gets you the answer. So mine was that the victim compares the length field to the max that it's going to permit you to store into its receive buffer when it's storing the commands you're sending at it to RAM. So what I did was issue 2 long 7816 commands to the victim, but otherwise I made sure the checksums were still good and watched the error response. And then this is to the point where I'm ready to start glitching. So then as I'm sending in these commands, I hit it with basically the first sucker punch, which you can see is you got your nominal clock envelope, and then you got your tiny little glitch in the middle. Or you can do the 1-2 punch where you hit it a couple times with the tiny pulse in the middle. And so this was clock glitching. And what I was doing was glitching during the suspected victim's command handler of the ISO 7816 commands coming in, and trying different pulse offsets when they start within the cycle and durations, how long the pulse is. And you'll reach a milestone when the victim responds to the 2 long command correctly. Like, it actually gives you a proper response, because now you know you've bypassed the length check, because it actually answers you even though you've sent in this crazy long command. Now you should be starting to think about your best guess at the victim architecture. And for most smart card or secure microcontroller type devices that aren't AVR or PIC or whatever, they're either going to be Motorola 6805, sometimes straight, sometimes heavily, heavily modified, or Intel 8051. So then what I was able to do was pad more and more bogus data at the end of the command, that fake validated command, until the victim crashes or does something weird. Now I'm pretty certain that I've smashed the stack, at least to the point where I've overwritten the return address. But it might be hard to notice if there's a hardware watchdog that actually catches the device crashing and reboots itself quickly, so you might have to be careful about that. And now you know the distance to the stack pointer from where the beginning of your smart card command buffer goes into RAM to where the stack pointer is further down. And now, using your guess at the victim architecture, you write minimal code that this is what I did, try to write to the low address special registers like port, pin, data direction register. Keep trying candidate return addresses at the end of that, because you know how far off into your payload the return address is. And so here's a quick graphic that just basically, and this is really even applies to x86 or ARM or whatever, right? You've got your payload, you overwrite your return address, and your stack's creeping back the other direction. So your next milestone is reached when the victim output pin changes all of a sudden, because now your port or your DDR or your whatever register you think you're trying to write to in different areas of the address space actually hits. And so now this is really good, because you've got code, you can confirm your code execution, and you can confirm your architecture guess. And it's probably going to be von Neumann or modified Harvard, because if it was like pure Harvard, you're probably not going to be able to see any sort of response like that. So now that you have code execution, I wrote code that loads a dummy ASCII byte, some tombstone value that I know, like 55 or whatever, to the desired, or actually a single character, to a desired register of memory, and then sweeps, jumps JSRs or whatever, or just jumps JMPs into increasing areas of address space, just looping over and over again, trying more of the address space. Although this could be unwieldy if you're using like a modern 32-bit processor where the address space could be huge, this might not be a trivial operation to complete in time. So your next milestone is reached when the ASCII byte pops out of the victim's serial pin. Because in this case, I was able to hit the serial transmit routine's address. I knew where it was because all of a sudden my byte popped out, the byte that I specifically sent in. So now you're getting really close. All you have to do is write code that loads data at each sequential address location, memory location into a register. Then you jump to your known serial transmit routine. Let's say if it's Motorola, it's the A accumulator or B or whatever if it's an older CPU core, and then it dumps that byte of memory through the serial transmit routine. And pretty much at this point, you have to be prepared to empty the FPGA UART's receive FIFO, because it's going to get clogged up with 9,000 tons of winning. And by winning, I mean code and data space, which is the in a von Neumann is pretty much the whole thing. So to wrap things up, the epilogue of this whole process is to be clear, you've got a dump of code and data space at this point, and now you can try and figure out the memory map. So just look at the dump for repeating blocks every now and then, so you can see where where there's mirroring present in the address space. Try poking values at different different addresses throughout that space. See if the address is mutable or not. So now you know probably if it's RAM or ROM, or you might know if it's flash or E², or you'll know if it's writable or not. So at least you can get a better idea. And now, most importantly, you're back in familiar territory. So you can hopefully already find an existing disassembler or make your own if you have to. You can search that disassembled code for crypto secrets, for serial numbers, for whatever, and of course discover if there's any vulnerabilities that are just already latent and sitting there in the code that you can now come through the front door with later on. So basically the conclusions of glitching in general, electrical glitching, is that it can be a viable attack vector against a variety of ICs, with the exception pretty much being some modern purpose-built security ICs where they're up to our tricks and they've put countermeasures at the hardware level. It's cheap to perform. You don't need a big laboratory. It's pretty much non-destructive in nature, except maybe your first initial few tries where you're getting a little crazy with the voltages. And it's another tool in the reverser's arsenal that can provide results where your other approaches have failed. So I'll try and speed right into, I'm not sure if there's any timer, if we can, okay. All right. So thank you everyone for paying attention or looking like you did.